In this Mathematica Sessions video with this guy, what we're going to be doing is looking at calculus and linear algebra problems that would be appropriate for someone doing a course in that topic. So it's maybe what you would think of as pre-algebra. We've got some problems in simplifying expressions, some problems on basic sets, some problems in geometry, and some problems in log rules and double angle formulas, angle addition formulas, and similar type problems. So that's probably appropriate for someone in a high school maths course or a first year university course at the early end of that. So if you're interested in that, then stick around. Thanks. Okay, well, let's begin our first problem. So this says, simplify the following showing the working. Okay, so we'll have a look at question A, and I'll do this in two ways. I'll do this by hand and then using Mathematica, and probably even Wolfram Alpha. Okay, so what we want to do with this one first is get a common denominator in this expression. So I'll just paste it here. Now what we want to do is multiply the left-hand term by x on the numerator and the denominator. So times x, and then x times x is x squared. So I'll copy and paste this over. Okay, now that we have that, let's put a bracket around this one on the right-hand side, and then we can add the numerators. Okay, so moving ahead, I want to take this over, and that will be subtracting from this numerator on the left. I can get rid of this now. And now all we have to do is simplify the rest. Okay, so taking this, now distributing that minus 1 over the bracket, we have minus x squared and then minus 2. Okay, but we can also multiply this one out, and so we'll have we'll have 3x and then plus x squared. So x times x, x squared, so copy and paste that there, and I can get rid of that bracket. Okay, finally I need to just add those in the numerator and cancel anything in the numerator and denominator when that happens. So these two are the same, so that will vanish. And then this looks to be simplified. Okay, so the next question you might have then is, how do I do this in Mathematica? And how do I do this in Wolfram Alpha if you don't have Mathematica on your system? So in Mathematica, I could just put factor or even simplify. So factor, and I get the same result, just with the minus 2 in front. Let's try simplify. So simplify. Okay, I also get the same thing. And now what if you wanted a step-by-step solution, or you didn't have Mathematica installed on your system? Then you could open that up on the website, the Wolfram Alpha website, but within Mathematica I can also open it up by putting two equal signs. Is that right? Or maybe I've forgotten how to do this, so let's see, do I come over in a new cell? Yep, there we go. I go in a new cell and do that, equals equals, and then I might type something like simplify, and then you've got to enter this in a way that you could do so easily on the website. So let's type this out in such a way, x to the power of 2 and plus 2, and then we would be dividing that by x squared. And then here I'm going to press Shift Enter, but I think on the website you can probably just press Enter or something. Okay, now this is giving step-by-step solutions, and you even get a plot of the function. Okay, and then your number of other things. All right, great. So let's get rid of this now. I'll go on this side cell and press cut. And then we'll come back up and look at our next question, which is actually down here. Okay, so the next one says simplify this division, basically. So by hand, what you would want to do, and incidentally, I should write turn this into a comment here, because that is just me typing the hand calculated solution out. Okay, so we'll do the same thing here, and then we'll later turn that into a comment. So this is the same as, now I've got a division sign here, so what I need to do is invert this fraction. Okay, so I'll do so by swapping the numerator and denominator there. So that was x minus 2 there, and then now I have a times, but I'll use an asterisk because it's easy to type. All right, great. Now I have some simplifying to do, or some cancellation. Right, now this assumes that x is not equal to 2 and not equal to minus 5, because otherwise we would have some zero denominators to worry about. Okay, so let's factorize the minus sign out of this one first, so we can see that we should cancel the x plus 5 in the numerator and the denominator. So I'll put a 1 here for this because I'm going to do that cancellation, and a 1 for this. Now also it looks like we're probably going to have an x minus 2 as a factor in the numerator on the left. So let's go ahead and factorize that quadratic, and then do the cancellation of the inevitable x minus 2 that we'll get here. Okay, so x squared, so we'll put 2 brackets. Okay, so one of those is probably x minus 2 because we have a minus 2 there. So the other one might be x plus 1. Let's just guess that. So if we expand that out, then we have a minus 2, and then we have an x minus 2x, which gives us minus x. So that actually works out fine. Okay, now we can perform the cancellation of the x minus 2. And so we'll just get rid of that in the numerator and the denominator and put a 1 there in its place. And so we can see that this is just minus x plus 1, which is minus x minus 1. Okay, great. And now let's turn this into a comment. And then we'll get Mathematica to simplify this. So I'll just write simplify, square bracket, and then I'll put that in, and we'll see what happens. Okay, great, it gave us the same thing. And again, there are a number of other ways to do that, like you could put equals equals, and then type this out. I don't know whether you might need to put this in as to the power of 2, okay, and then run that. We'll see what happens. You might have to have the divide sign, but this seems to work anyway. All right, so, but my advice is type it in a way that's compatible for Wolfram Alpha to read. And so you get all the step by step and some graphs. Some maybe a little bit too much to look at. Okay, so let's cut this now, and let's have a look at the next question. So this one says simplify this. Let's just call this a nested fraction. Okay, but if you, it's actually a continued fraction, the continued fraction of a rational number. So how would we want to do this by hand? Okay, so we would probably start at the bottom. So this is equal to, now let's see, this here is 1 over 2. Okay, and so next we would add 1 and 1/2 at the bottom. And we would have 3 halves there. Okay, so now we've got 1 over 3 halves, but that is actually 2/3 there. So let's put 2/3. Okay, now 1 plus 2/3 is 3/3 plus 2/3, which is 5/3. So let's replace that with a 5 there. Okay, now we've got 1 over 5/3 to deal with, and so that's 3/5 here. So 3 over 5. And then finally, 1 plus 3/5 is 5/5 plus 3/5, which is 8/5. All right, we'll make this a comment, and then we'll go ahead and do this on the calculator. So I can just copy and paste this. And incidentally, you can enter that using the palettes. So I would just go up here and run palettes, basic math assistant, and use this fraction button to enter that. Okay, so now if I want to calculate this, shift and enter, and I get 8/5. Of course, you could do this also in Wolfram Alpha. So I'll open this in a new cell. And let's see how I would do this. I would write 1 plus, and then 1 over, and then in brackets for the denominator, 1 plus, and then 1 over, and then a bracket, 1 plus 1 over, and then our final denominator looks to be 1 plus 1. Now, I think I have 8 ones in this picture here, so let's count them. 1, 2, 3, 4, 5, 6, 7, 8. That looks good. Let's press the button and see what we get here from Wolfram Alpha. Okay, so it gives us 8/5 and a decimal number and some other things. Continued fraction, Egyptian fraction, expansion. Okay, so this continued fraction is the continued fraction of a rational number, which incidentally, since it's rational, that's not unique. I think there are multiple ways to write that. Okay, so let's now cut this and move on and have a look at another one. Actually, why don't we just add to this question? So, because it goes into continued fractions, so let's just add another question here. So what if we had x equals, and then instead we had plus dot dot dot, a diagonal dot dot dot, so under the assumption that that keeps going. So how would you do that? Well, we've set this as x. Okay, so the next thing we want to do is subtract 1 from both sides. So let's go ahead and do that. So x minus 1 then is 1 over 1 plus dot dot dot. And so where we're going with this is we're trying to view this as x, right? So this is in fact x. So we can go ahead and just replace that now with x. So we would want to solve this equation for x, which is an equivalent problem. Okay, so then by hand I would multiply both sides by x, and I would get x squared minus x there on the left, and then I multiply that x away onto the left, and then I would want to subtract 1 from both sides, and I'd have 0 on the right hand side, and then now I need to solve this, right? Okay, so I can use the quadratic formula, I can factorize this, but this probably involves maybe even the square root of 5. Okay, so I'll turn this into a comment, and now I'll show you how to use the computer to help you solve that. Okay, so let's just write solve this, and we're solving for x, but don't think we need to include that. So yes, I was right. This involves the square root of 5, and from memory, these are golden ratio numbers. So now if you wanted to view those in terms of the golden ratio, let's just take the numerical solution of this. So if I put an n in front of that, n solve, then I get minus 0.618, etc., and 1.618, etc. All right, so those are golden ratio numbers. I never remember exactly which is which So that's the reason why I call them just golden ratio numbers. Okay, so right, so let's move on. Can you add 4 consecutive integers to produce a multiple of 4? Use algebra to show and explain your answer. Okay, so let's say that the first one is a. So a, and then the next one, since they're consecutive integers that we're referring to, a plus 1, and then plus a plus 2 would be the next one. Okay, now we have 3 of them, and a plus 3 would be the fourth one. Okay, to produce a multiple of 4. So let's say this would be equal to 4b, where b is an integer. Now to set this out properly, let's say something like assume a and b belonging to, so I'll pull up a palette now. I'll just use the appropriate mathematical symbols. So I want this symbol for belongs to, and then I want the double struct z to represent the set of integers here. So assume there exist a and b belonging to the set of integers such that, and I like to use a colon for such that when I type this out. Okay, so given that we've got our hypothesis here, let's simplify this. So what does this mean? Now, if we just simplify the left-hand side, then we would have 4 of the a's, and then 1 plus 2 plus 3 is 6. So plus 6 is equal to 4b. Okay, so now the next word we would write is then, and then a full stop or a period if you're in the USA. Okay, now let's simplify this algebraically. So then we have 4 bracket b minus a factorizing the 4 out of the expression. And so that's equal to 6 doing the algebra there. All right, now we'll quickly see that this is contradictory because dividing both sides by 4, we have b minus a is equal to 3/2, right? Simplifying 6 over 4. Okay, which is not an integer. And since we know that b minus a should be an integer, this is a contradiction. So just put a C exclamation to mean a contradiction. So the conclusion is no, we cannot add 4 consecutive integers to produce a multiple of 4. No. Okay, let's make this a comment because all we did is do some typing there. Okay, let's have a look at the next one. State whether the following statements are true or false. Explain. All right, and I'll give some space between this and the next question. Okay, so here I didn't quite have the right symbol, but what I want is this subset symbol with a horizontal line under it to mean a subset or equal to. Okay, so here we have A is a subset or equal to B, where A is the set of multiples of 6 and B is the set of multiples of 2. So let's just write out what these sets are. So in this case, A is equal to multiples of 6, but if I just grab this symbol here, we could write this 6z, meaning multiples of 6. All right, but let's just discuss what's in this set. So if we've got minus 15 in it, so dot, 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 comma, minus 15, then minus 12, then minus 6, then 0, then 6, then 12, then 15, then 18, and then dot, dot, dot. So these are the multiples of 6 going in both directions. Minus infinite, plus infinite. Okay, now what about B? So let's do some copying and pasting here because B will look similar. So B is the set of multiples of 2. Okay, so we'll write that 2z, and then we might put minus 6, minus 4, minus 2, 0, 2, 4, 6, 8, and so on. Okay, so the even numbers now, is A a subset or equal to B? Well, the answer is clearly no now that we see what's in this. No, because since minus 6 belongs to A, but minus 6 does not belong to, I'll just put it as not in B. Okay, so this one's false. And all of this is just a comment, not code. Okay, next one. If D is equal to the set of all real numbers x such that x squared is 4, then D is equal to the set containing 2. Well, this is clearly false, right? Because if we just solve this equation, then we get x is plus or minus 2, and both of those are real numbers, so D is equal to the set containing minus 2 and 2, all right? And this is different from the set. So I'll put not equals the set containing 2, so false. All right, and this is also a comment. Now the question C says if the set E is equal to the set of all real numbers such that R is equal to 2R, and actually this should be the set of all real numbers R such that R is equal to 2R, then E is equal to the empty set. Okay, well, let's restate what the set E is, right? Because we can do some simplifying here. So taking this R to the other side of the equation, we would have minus R there and 0 here. 2R minus R is 1R. Okay, so this is R equals 0. And what is this set? It's just the set containing 0, right? Now, this is not the same. So I'll say not equals the set with nothing in it, which is the empty set. Okay, right, so these two are not the same. So this is not the same as this. And so this one is false. Okay, so that's a comment as well. All right, let's move on. So get rid of this gap here. Now we've got a geometric question. Find the angle ABF. So that's over here on the left, I think. Let's just assume that it's this because I don't know really how you're meant to write these angles. I think it talks about this angle right here, so that's what I'll work with. And the length BF if the regular hexagon below has side length 1. Okay, so a regular hexagon is a hexagon in which all sides have equal length and all interior angles are the same. Okay, so what I want to think about with this one is I want to call this angle here at A alpha, and I want to call this angle up here beta, and I want to call this one down here at F beta, as in on the left-hand side of that vertical line there. Now this, we'll just assume that this is a 90-degree angle here on the right-hand side at F, and likewise up here on the right-hand side of the vertical line at B. So I'll work in radians. Okay, so what I want to write here is that, actually I said alpha and beta, but why don't we just call those A and B? So lowercase a and b. So that would be A plus 2B is equal to, that would add up to 180 degrees, but since I want to work in radians, then that adds up to pi radians. So I'll pull up a pi out of the palettes just to keep it looking pretty. Here we go. All right, so we've got that. Talking about the sum of these interior angles on this triangle. Now, what about another expression for this? Okay, so we can also see that the angle B in here plus 90 degrees, which is pi on 2, will also add up to a, right? Because that's the same angle as a. Okay, so let's write b plus pi on 2 will add up to a. And now what we need to do is solve this simultaneous equations here. Okay, so I can do this by hand, but I'll also show you how to get Mathematica to do that for you. So I'll take the second one and I'll just write that as b equals a minus pi on 2, and then we'll sub into the second equation up here, or sorry, the first equation there. So I'll take this, I'll put it right here, and we'll say sub in. Okay, so that's what we're doing, and now we need to expand the left-hand side and simplify this. Okay, so again, working by hand, so simplifying. What we have then is 2 of the a's there, and we just cancel the 2 there. Okay, so that gives us 3a on the left is equal to 2 of the pi's, taking this minus pi over to the right-hand side. And now finally we want to divide by 3. So a is equal to 2 pi on 3 radians. Okay, can we get a corresponding value for b? Yes, let's just use this. Okay, so b is equal to a minus pi on 2. Now we know a is 2 pi on 3, so we just need to take this difference. So we need a common denominator here, and let's let that be the product of 3 and 2, which is 6. So we've got 4 pi multiplying this first one on the left by 2. So 4 pi on 6, and then minus 3 pi. Okay, so that's all over 6. Simplifying this, we just have pi on 6. Get rid of this bracket. Okay, so b is pi on 6 radians. Now, what I want to imagine here is that, okay, so we've got b, this little angle up here on the left of the vertical line is pi on 6. Then let's imagine we've got a horizontal dotted line through here following my mouse cursor, and I want to just divide that angle a by 2. So the angle that I'm thinking of then is, well, half of 2 pi on 3, which is pi on 3. Okay, so let's think about this. A on 2 is pi on 3. And then let's just rewrite that b is pi on 6. Okay, good. So now that I have that, the corresponding length, because remember we want the length of this BF, so half of that length is, let's just call it L. Is L a good letter? No, let's just call it something else. How about BF for F? Okay, so 2F is the length of the vertical segment we want. Okay, so really I want to solve for F then, right? So F is half of that. And I'm imagining a triangle here in the upper left area, a right triangle. I'm not going to draw it here. I just want to be quick about this. Okay, so then what we have then is F over the hypotenuse length, which is 1, is equal to the sine of the angle A on 2. Okay, so now since we want 2f, we'll multiply this by 2, so 2f then is equal to 2 times sine of a on 2, but we know a on 2 is pi on 3. Okay, so this is the length we want, which is, well, let's just write length BF equals this one, and then we just need sine of pi on 3. But the sine of pi on 3 is the square root of 3 over 2. So this is root 3. So I'll open up the palettes and grab a root sign. Okay, so root 3 on 2 times 2 is root 3. Okay, good. So we have answered that. So our answer then is A equals this, and length of BF is equal to the square root of 3. I'm going to save this now. And all of this was a comment, so I'll turn that into a comment, because there was no real code involved. Okay, let's have a look at the next question. Simplify the following. So these are just algebraic simplifications. Okay, let's have a look at this first one. Now we'll do this by hand, and then we'll get Mathematica or Wolfram Alpha to do the same. So this is equal to, now we've got a negative sign in the exponent, so we want to invert that fraction and write that as a positive 3/4. So I'll have 16 on the numerator and 81 on the denominator, and then we change that to the opposite sign. Okay, next we want to represent the, because we can see that 16 is a power of 2, 81 is a power of 3, so let's just write those as their respective powers. So this is, 16 is 4 times 4, which is 2 to the power of 4. 81 is 9 times 9, or 3 to the power of 4. And so what we see then is that this is 2/3 to the power of 4 inside the bracket. So I'll open up a palette again. I keep closing this because it's kind of getting in the way, but I seem to need to open it again. Okay, so 2/3 to the power of 4. And now we want to use an exponent rule that says we can just multiply these exponents. We have a to the power of b all to the power of c, so that's a to the power of b times c. Okay, so 4 times 3/4 in the exponent. I can get rid of the extra bracket there. Now we want to simplify that fraction in the exponent. So we cancel the 4, and that's just to the power of 3 now. Okay, and we can simplify this because 2 cubed is 8, and 3 cubed is 27. So we have 8 over 27. This is a comment, and now I can get Mathematica or Wolfram Alpha to do the same thing. Okay, so probably I can just put it there and press Shift and Enter, and I get 8 over 27. But if you opened up Wolfram Alpha, so let's do this, and type that in the way you might do that, 81 over 16 to the power of, now I need a bracket, minus 3/4. I'll press the button. It'll get on the internet and hopefully give us something. Okay, so same result, and we also get a decimal expansion and number line and other things, continued fraction and so on. Great. Okay, let's close that, cut it. Okay, the next one is simplify this algebraic expression. Okay, that's relatively easy. Let's go ahead and do that. This is equal to, let's see, we've got 2 of these x's to add. So we'll add those exponents. So that'll be to the power of minus 2 there. 2 plus 1 is 3. Okay, now when we're dividing, what we can do is change the sign of this denominator here by putting minus signs there. But first, we can add the exponents. So 3 minus 2 is plus 1. Okay, but what I was going to say is that you could make this times y to the power of minus 1. Now, it's a bit unnecessary here because we can just divide that straight away. And subtract the 1 from the 3 and get 2 there. Okay, now that's the final solution there. And you could even put y over x all squared. So let's write that. Y over x to the power of 2. Okay, we'll make this a comment and then we'll get Mathematica to simplify that. So simplify this, and I think what I need to do is put a bracket here. I'm not quite sure. There we go. Y squared over x squared. Great. Okay, next, calculate the following trig ratios. So when we do this, I recommend strongly that you draw some corresponding pictures. So I'm going to do that for the second and third one here. All right, so you've got to think about where is this angle, and then think about the trig ratio of the angle. All right, so 3 pi on 2, now that's pi, which is 180, plus another 90 degrees, or pi on 2. So pi plus pi on 2 gives 3 pi on 2. So counterclockwise from the positive end of the x-axis, and that takes us into the third quadrant. So you want to think of this as sine of pi on 2, right? So sine of pi on 2 is 1, but the position of this being in the third quadrant means that this one is minus 1. Okay, so I'll just say, just write that down straight away. This is minus 1. That's the comment. And now let's just ask Mathematica to verify that. Shift and enter, minus 1, that looks good. Okay, next one. Now, like I said, we need to draw a picture of this, but first, before you can draw a picture, you need to work out where this angle is. From the positive end of the x-axis, counterclockwise around. Okay, so 3 pi on 4. Now, that is pi, so 180 degrees minus pi on 4, so minus 45 degrees. So I'm imagining a 45 degree angle with its base on the negative end of the x-axis. Okay, so that's what I've drawn here. So I'll import it and show you, and we can make this a little bit smaller when we're ready to work. So we come around here from the positive end of the x-axis to that angle, and then we consider the triangle within this with the base on the axis. Okay, now here I have ASTC, or I like to think of the acronym all stations to central, as in trains, but it really represents all functions, then sine and tan and cos, being positive in those quadrants and the rest negative. So in this quadrant, sine is positive, but cos is negative. So we expect to get something negative here. All right, now we're considering the cosine of this angle pi on 4 here, which is adjacent over hypotenuse. So 1 on root 2, but considering that this is in the second quadrant, we've got minus 1 on root 2. Okay, so let's just say that. Minus 1 on the square root of 2. But we can multiply numerator and denominator by root 2, and then that gives us a rational denominator. And so we would have root 2 minus root 2, over 2. Okay, now let's get Mathematica to do the same thing. And it gives us exactly that. So I'll just grab this and I'll copy it and make this look pretty there. Okay, so I've got the root 2 there in the numerator now in this form. Okay, good. Let's make this small. I'll just grab it and minimize the size of it with my mouse. And let's have a look at the next one. So now we're going to calculate tan of 7 pi on 6. So 7 pi on 6 is more than pi, but it's more than pi by pi on 6. So in other words, pi plus pi on 6. So we can view this as beyond the negative end of the x-axis by pi on 6. And we want to draw that by hand, but I'm just doing it here with paint and importing it because that's really easy to do. And this is the triangle here that I want to imagine. With its base on the x-axis there, it's in the third quadrant, so coming around from the positive end of the x-axis all the way to 7 pi on 6 radians. Okay, brings us right in here. So this is pi on 6 beyond the pi radians. So this is the angle here that we're interested in. Now, we're interested in the tangent ratio there, which is opposite over adjacent. Okay, so 1 on root 3. Now let's consider the sign of that. Is it positive or negative? Well, tan is positive here, so that should be positive. Okay, so the answer then is 1 on root 3. I'll just grab this because that'll look nice, and then I'll change the 2 to a 3. And I'll come and write that here. Okay, so tan of this is equal to 1 on root 3. That's a comment though. Now I want to get Mathematica to do the same and verify that for me. I'll make this image a little smaller, and then I'll just put this underneath and calculate. Okay, great, it gives 1 on root 3. Okay, let's have a look at the next one. Use a machine. Now this problem could say use a calculator. So you could do this with a calculator too, or you could use Mathematica to do this. But I'll point out an important distinction first between a calculator and Mathematica. All right, but the problem says between for theta between 0 and 2 pi. Okay, because there are multiple solutions of this if you allow it to go outside of 2 pi. Remember, these are periodic functions of period 2 pi. All right, so what you do on Mathematica first is you would write, you want to take the inverse function and apply it to both sides. Now, we know the inverse function as arctan. So arctan with an uppercase on the t. And what I need to put in is 0.25, okay? So let's press the button and we get 0.244979 radians because this is the default here. Okay, but if you wanted this in degrees, we might set this in memory as t for theta, for example, and then to change to degrees, I would want the radians symbol, which is invisible there, but I would want that to cancel. So I want t times 180, or you could do this in terms of 360, but I want the radians to cancel, so they're pi radians corresponding to 180 degrees. Okay, and so here we go, and I have 14 degrees, roughly. All right, sure, but if you're working with the calculator, then the calculator has this funny symbol. You would put in something like, I'll get the palette to represent this here. So, and I'll write this also. On calculator. I spelled that right. So it's typically something like this to the power of -1, and then you would put this in 0.25. Right, but take care there because this typically refers to 1 divided by something, right? When you put to the -1, but here it means inverse function. So there's possibly some ambiguity here. I like arctan better because it really suggests that you're taking the inverse function rather than 1 divided by. Okay, moving on. So do the same with 0.37. So again, we just take arctan of minus 0.37. This is what we have in radians, but if we want to convert that, then it's pretty easy to do. We just multiply by 180 over pi. And we have minus 20.3 degrees roughly. Okay, next we have a proof to do. Prove the sine and cosine rules using the diagram below. Alright, so the diagram's not the best in that that little lowercase c there is right under the dotted line, so probably should have been shifted over to the left, but it's the distance between this as point A and point B, right? So the length of that base there. Okay, so prove the sine and cosine rules. So the first thing we want to do here to do that, and our aim here is first to prove the sine rule, is we want to represent the d, this lowercase d here, the vertical dotted line, the length of that segment in two ways. And so if we have it in two ways, those two ways are equal. Okay, so let's see. D over B will be equal to the sine of the angle A. Alright, so I'm thinking of the angle A here when I write this. And we can multiply both sides by B, so that D is equal to B times the sine of the angle A. Okay, similarly we can do that on the right hand side here with the angle B. And what we'll have is that D is equal to the hypotenuse A times the sine of the angle B. Okay, now we can just equate the two D's. So B sine of A is equal to A sine of B. And then the sine rule says that sine of A over A is sine of B over B. So we want to rewrite this in that way. Sine of A over A is sine of B over B, which is the sine rule. Okay, so that part's done. I'll turn this into a comment, and then I'll work on the cosine rule next. Alright, so with the cosine rule, what we want to do here is introduce some coordinates for points, right? But we want to keep this simple. So now I want to view A as a point. So the point A, so we'll say let A be equal to the origin, which would be the point 0, 0. Okay, let's let B then be equal to, let's see, so B would be having x coordinate C, lowercase c, and y coordinate 0, and then uppercase C is a little bit more complicated, but it is, let's see, now we need a cosine here, don't we, for the x part of it. So cos, or the hypotenuse is B, so B cos of the angle A, that's the x coordinate there. Now the height of that is the height we already worked out as B sine. So B sine of the angle A when we did the sine rule. Okay, so we've got these. Now we want to express A in terms of, well, vectors. So think vectors now. So the vector BC, and I want to put an arrow over the top of that, so I'll open the palette again and find an arrow or something like it. Here, I want something like this. Okay, that'll do. So this is the coordinates of C minus the coordinates of B, which in this case is this minus minus this point B. Okay, now we'll simplify that difference. So we basically have this, except for in the x-coordinate there's a minus c there. Okay, now I have the vector description of the vector BC. So how do you get from B to C? Well, you take this, add this onto it. Okay, now I want the norm of that vector, right? So typically we would write two vertical lines, but I'll stick with one. It'll be pink because this is not appropriate syntax here if I were coding. So this is the norm of this vector here. Okay, and then I would take the square root of the sum of the squares, right? But why don't we just square both sides? So the square of the norm here is the square of this norm, which is just the first coordinate squared. So I'll get rid of this. So this squared plus this one here squared. Okay, but what is this? The norm of the vector BC squared is a squared. So a squared is equal to this. Okay, now all we have to do is expand this right-hand side. So let's put that down below. Okay, so expanding this, then we will have b squared and then cos squared. So I'll put the squared after the bracket. And then minus the product of those two, but what we had inside was, okay, so b cos, so it'll be minus bc, but we've got two of those when we expand that out, and then plus minus c squared, which is c squared. Okay, so that's that part, and then let's expand this, so sine squared, and then we'll have a b squared as well. Great, now we want to rearrange things and simplify. I can see I need a space there. Okay, so let's put the sum of the cos and the sine together, because we know there's a special rule for those. And we'll factor out the b squared so we can see that clearly. Okay, sine squared plus cos squared is 1. So we can replace this here in the bracket with a 1. And so we just have b squared for that part. And then let's put the c squared next to the b squared. Okay, so we found out that a squared is equal to b squared plus c squared minus 2bc cos of a. Okay, that's the cosine rule right there. And now all of this is a comment, so let's turn that into 1. And I'll save this. Okay, next and almost last question for this problem set. Use an angle addition formula to calculate sine of pi over 12. Okay, so we want to view pi over 12 as a sum of two angles that we know that we can calculate an exact or a surd value for the trig ratio. So let's put that this is equal to, now 12 factorizes as 3 times 4, right? So that's an obvious choice for denominators. So I'll copy this, put a plus here, I'll put a 3 there, and a 4 there. And just see, does that add up? Well, they've got a common denominator of 12 when we cross multiply, but we would get 7 pi on 12. So actually we want a minus sign here. Okay, so sine of pi on 12 is equal to this. And now we want to use an angle addition formula, but in our case, this is a difference, right? So what we have then, and okay, so we've got sine of pi on 3, and then we've got cos of pi on 4. So turn this into a cos. And then we swap these around, okay? So, and it's a minus between them. So I'll change these. Yeah, so we swap the angles in those. Okay, now these are things that we can calculate exactly. Okay, because we know then that Sine of pi on 3 is root 3 on 2. That's right, sqrt 3 over 2. I need a bracket because I've written it in that way. Okay, and then cos of pi on 4 is 1 on root 2. Sine of pi on 4 is 1 on root 2. And then cos of pi on 3 is 1/2. Okay, great. So now we can simplify this and get an exact third representation of that sine ratio of pi on 12. So the numerator here is root 3 when I multiply that out, and the denominator is 2 root 2. So I'll put that there, and I'll get rid of this. Okay, now this denominator is also 2 root 2, but the numerator is 1. So that means then that we have in the numerator here root 3 minus 1 all over 2 root 2. We can get rid of the extra brackets there. Okay, great. So that's complete. The next one says use this to calculate cos of 5 pi on 12. Okay, let's do that. Now 5 pi on 12, so we can view 5 pi on 12 as, in terms of pi on 12, as, let's see, so what would it be? Plus pi on 12. So we would have a 4 there. So 4 on 12 would be 1 on 3, right? Okay, is that something that we can take a trig ratio of exactly? Yes. And by exactly, I just mean in terms of a third. So we need an angle addition formula for the cosine. All right, that's pretty simple. Hopefully we remember this. It's product of the two causes and then a difference of the two sines. Okay, so I'll take a minus there, and I'll replace the cosine with the sine. Likewise there. Okay, great, and then we want to simplify this. So put this underneath here. So, cos of pi on 3, that's 1/2. Cos of pi on 12. Okay, so in a similar way, this is going to be 1 plus root 3 all over 2 root 2. Okay, so just to save doing that again. And so sine of pi on 3 is root 3 on 2. So square root 3 over 2. And then this one we've already calculated above as this difference up here. Okay, and so you could simplify all of that. Now I'm just going to get the computer to help out with that. Supposing that I'm feeling a little lazy, let's do that. So just copy and paste that after I turn the above line into a comment, and then I'll just press the button. Okay, and now we have a nice expression, except perhaps it's not as nicely factorized as we want it. So I could write simplify here in front of it. And now I have root 3 minus 1 over root 2. Okay, great. Now, next one, find all real solutions to the following. Okay, so we want to use some log rules for this one in question A. So the sum of two logs is the log of their product. Okay, so just do that. I'll put brackets around this. And now both of these are to base 2, so I can look at the insides and say that these insides must be the same. Okay, so this equals 10. And now all I have to do is solve this quadratic equation. But that looks fairly simple. So x squared, let's see, minus x when I add that together. And then I'll have a minus 2 minus another 10, which is minus 12. All right, and now we want to factorize this. So we'll have x plus 3 and x minus 4 multiplies together to give this quadratic here, and so this is equal to 0. Likewise, this one was equal to 0. Okay, so that gives us two real solutions. X is equal to minus 3 or plus 4. Okay, so there are two real solutions there. Now, there are also complex solutions, right? And that gets a little bit tricky. But what I want to show you is, now I'll turn this into a comment here. What happens then when you go and substitute back in minus 3 into this expression on the left here? Do you get log to base 2 of 10? So I'm going to write replace all, but in shorthand, what I can do is just put a slash and then a dot, and then I'll say x minus greater than, and then press the space bar, goes to minus 3. Okay, now I'll press the button. Oh, right, I see. So this is not exactly Mathematica syntax. I need to put the 2 comma there for base 2, and likewise here. All right, let's do that. And now you can see I get a complex number in here, right? Which makes you scratch your head for a moment until you realize it's okay. So that's pi times the square root of minus 1. Okay, so we're not getting a real solution for the left-hand side here when we go and substitute in minus 3. So what's the go? Now I'll show you. Let's go ahead and factorize this. Factor. Okay, so we have this, but when you're dealing with logs, now we've got a sum of two logs here, right? So that's log to base e, because it's changed this to base e, but log to base e of 10, and then, so let's just rewrite this. So we've got that, and then we can express that as plus log to base 10 over log to base 2 there, and we've already taken out that imaginary part. All right, but a log rule says that this log to the natural base is actually log to base 2 of 10. So I'll go ahead and copy this, paste it, and I'll just go ahead and put the 2 back in there. So this is what we have here, right? So this part's fine. This is the real part. But what about this? Okay, so this is actually okay because we've got this identity here. So I'll just write e as in 2.71828 and so on, e to the power of 2 pi I. All right, so that should be equal to 1. Because e to the power of 2 pi I is 1, this all works out, and it's not actually a problem. Because if you take the natural logarithm of in this expression, what you have is that 2 pi I is equal to the natural log of 1, right? Okay, sure. So that's all fine there. That's not a problem in solving that one up here and getting a minus 3. Okay, now next one. We have a sum of 2 logs to base 3. Okay, so we're going to take the product here of those. So that'll be log to base 3 of x cubed is minus 6, and then the log rule says that we can pull this 3 down and put it in front. Okay, so we'll do that next. So we have the 3 there. Now we can divide both sides by 3 and get minus 2 there. And now that says x is equal to minus 2 or 3 to the power minus 2. Okay, which is 1/9. Great, good. And so we can also get Mathematica to verify this for us. So you could write replace all, but what I'll do is just put the slash and the dot, and then x goes to 1/9. Okay, great. And then I want to press simplify here. So simplify. All right, I see. I've done this again. Sure. So 3 comma that, 3 comma that, and then if you don't believe that, you can just take a numerical value and get -6. Okay, good. Let's have a look at the last question here. So solve this equation. Okay, so let's see if we can just get Mathematica to solve this one for us. If I just write solve, now I've got to change and put the base in properly here. And likewise here, put the base in. Okay. It says the tag is protected. Okay, that's because I put the wrong equal sign there. Let's try that again. Now it says x goes to 3, so that's our answer there. Okay, so that works. Now let's do this by hand. So log to base 10 of 1/10. I want to view this as 10 to the power minus 1. Okay, and then I want to pull that -1 down using the log rule. So this is minus log to base 10 of 10, which is -1. Okay, and then I want to add 2 to both sides of that expression. So 2 minus 1 on the right-hand side, but this logarithm on the left-hand side. So 2 minus 1 is 1. So I've got log to base 10 of 10x over 3 is 1. So that says that the inside part of the function is equal to 10 to the power of 1. Okay, which is 10. But now we've got, dividing by that 10, we've got x over 3 is equal to 1. So x is equal to 3. Great. All right, thank you for watching, and I'll see you in the next one.